All right, good morning. Welcome. Today we are going to be talking about the relationship between voltage, current, and resistance. We are going to be looking at how those relate to each other and how we can solve those in a circuit and how we could solve for different values that we'll have in a circuit. All right, first of all, let's just talk about what voltage, current, resistance, and power are. The current is actually the amount of charge that moves through a circuit in a given time. It's the flow of charge in a circuit. If we were thinking about a pipe with water in it, this would be the water that's actually moving through the pipe. So the water that moves through a pipe is similar to the current that flows through a wire in a circuit. Now, just like a pipe would have to have pressure to force that water through the pipe, the circuit has to have pressure or push in order to force the charge through, and that push is voltage. So voltage is kind of the electrical push that forces charge to move through a circuit. Now, just like in a pipe, the water doesn't get to move freely without any friction. In a circuit, in a circuit, charge doesn't get to move freely without any resistance. Electrical resistance, electrical friction is called resistance, and that's how difficult it is to force charge through a circuit. Now, we've talked before about power as the rate at which work was done or the rate at which energy was used, and specifically for this unit on electricity, power will be the rate at which electricity is used. Let's see, just to add a little bit in there, current, the symbol for current is a capital I. Oh, let's erase that. Here we go. The symbol for current is a capital I. And so a capital I is what we're going to use to identify current. And the units are going to be amperes. And so you might see written in our givens off to the side, I equals 5A, and that would mean that the current in a circuit was 5 amperes or 5 amps. Voltage, the symbol for voltage is a V, and the units are volts. Voltage is actually something in physics that voltage, the symbol is a V, and then the unit is volts, and the symbol for volts is a V. And so voltage is one of those few things where everything starts with the same letter and matches all the way across. So that's kind of nice. The symbol for resistance is an R, and the unit for resistance is ohms. Now, the symbol for ohms is not an O, at least not an English O or Roman O. It is, in fact, a Greek omega. And so this is a capital Greek omega, and that's the symbol for ohms. And so you might see R equals 15 ohms, and that would tell you that your resistance was 15 ohms in that part of the circuit. And that is just a measure of how difficult it is to push that charge through there. If you have a resistance of 5 ohms, then that's less resistance and it's easier to force charge through than if it's 15 ohms. So that's just a measure of how hard it is to push charge through the circuit. Power, yes, bless you. You're now permanently memorialized in the video. Congratulations. Power is symbolized by P, and it is the rate at which electricity is used. Does anyone in the audience remember what the unit is for power? That's right, it is watts. And so the unit for this is watts, which of course is symbolized by a capital W. All right, and I'm going to pause the video just for a moment, give everybody a chance to finish copying down anything they need to, and those of you watching at home can feel free to do the same. All right, and we are back and continuing. And if we move on, let's see. Let's look again at the relationship between voltage, current, and resistance, but let's look at it mathematically. Mathematically, this is how we'll represent the relationship between voltage, current, and resistance. And of course, there's a little multiplication dot in there. This is oftentimes called Ohm's law. It's not exactly Ohm's law, but it's a mathematical relationship between voltage, current, and resistance. I will probably go ahead and call it Ohm's law, even though it's really not. That's okay. Don't worry about it. It'll be fine. Let's see. So let's talk about what if we had a particular circuit. Now, if I want to draw a circuit, if I want to represent a circuit with a diagram, remember that there's a few things we have to have in a circuit. The first thing we have to have is a voltage source. So I'm going to draw this, and I've got a tall line and a small line, and that represents our voltage source. This is the positive side. This is the negative side. And this might be something like a battery or some other source. We're going to say it's a battery. And we are going to label that. Let's just say it's 12 volts. So I'm going to label this as a 12-volt voltage source or 12-volt potential source. Remember that voltage is a form of energy. It's a form of potential energy. And so you can use voltage to do stuff like light up a light bulb, run a motor, turn a fan, all kinds of things, run a screen, run a speaker. And so here we have a voltage source that we're going to use to do something. Now, I'm going to draw the wires in our circuit like this, just with a line. And so that line is representing the wire in the circuit. And then I'm going to come here and I'm going to draw a load. In this case, I'm going to draw a resistor. And we just draw it with a squiggly line to represent that, just like if somebody were running down this and this is a nice smooth straight road, well, here they come to a place where things are a little crooked, and so they couldn't move through there as quickly. So that's how we represent a resistor. And so we're going to say that there is a resistor, and let's just give that a resistance of 4 ohms. So here we have a circuit. Remember that to have a circuit, you have to have a complete conducting path from one side of the voltage source to the other side. So we've got a complete conducting path from the positive side through the resistor and to the negative side. And it's a 12-volt voltage source and a 4 ohm resistor. And the question is, how much current is there moving through this circuit? In other words, I've got some current that's leaving this battery and moving through the circuit and then returning to this side of the battery, and I want to know how much it is. Now, let me go ahead and make an important point at this point in the video. The amount of current that's moving through all parts of this circuit is the same. Let me say that again. That's really important. The amount of current in all parts of this circuit is the same. In other words, however much current there is here, we've got the same amount here, we've got the same amount through the resistor, and we've got the same amount returning to the battery. And that's because charge is conserved. You can't have more in one part of the circuit than the other. And so the amount is going to be the same. And my question is, how much? Well, in order to calculate how much, we need to apply the mathematics to the circuit. And so I'm going to write down V equals IR. And here's my question. Let's see. How many volts do we have? All right, well, we've got 12 volts. How much current do we have? That's what we're trying to find out. And so we're going to leave that as a letter. And how much resistance do we have? Yeah, we have 4 ohms of resistance. So I'm going to put that 4 in here. Okay, and the math is super easy here. Take 12, divide by 4, and we're going to get a current of 3 amps. And that means that 3 amps of current are leaving this battery, flowing through this circuit, that's how much current is flowing through this resistor, and then 3 amps are returning to the battery. Just like in a pipe, you can't have more water moving through one part of the pipe than you have moving through another part of the pipe. Okay? You have to have the same flow rate, the same gallons per minute through all parts of the pipe. And so this would be the same number of amps through all parts of the wire, since there's nowhere else for it to go. All right. And so that's all that there is to that. My next question is, though, how fast is this circuit using up electricity? And for that, we're going to need to calculate the power. So I want to know the power that's used up by this circuit, and specifically by this load. The wires aren't using up any power. It's the load that's using up power. And so we're going to, for that, we're going to use a new formula. And this is the relationship between power and current and voltage. P equals I times V, and that's the rate at which power is used. All right, well that's not any harder than finding the current was. And in fact, let's see, the first thing that I'll need is the current from my previous question, 3. What's the voltage here? Still 12. And so the power is, in fact, 36 watts. And so those are the two things that you're going to be asked for very often. What is the current in a circuit, and what is the power used by the circuit? And all you have to do is apply the math to it. You use that calculation in order to calculate voltage, current, or resistance, and you use this calculation in order to calculate power. All right, I tell you what, let's look at what would happen. What if I had more than one circuit, or more than one resistor in a circuit? So I'm going to pause it for a moment and see if there's any questions here in the room, and then we'll be ready to continue. All right, and so we're back. One question that came up that I want to emphasize: the amount of current that leaves the battery is exactly the same as the amount that returns to the battery. And so if I have 3 amps that are leaving the battery, I have to have that same amount returning back. And since there's only one wire through the rest of the circuit, the amount has to be the same through that wire. It's as if we had one pipe and it were already full of water. If you had one pipe already full of water, you couldn't put more in one end than you get out the other end. And so however much leaves the battery has to be the same amount returning to the battery, and it has to be the same amount moving through the rest of the wire. All right, so just to re-emphasize that, and let's look at what happens. What if we have more than one resistor? Now, if I have more than one resistor, let's just say 2 resistors, and the question is, what happens with them? Well, there's a couple of ways to arrange 2 resistors. One is with them in line, one right after the other. There's resistor 1, there's resistor 2, and then back to the battery. And I'll just label those resistor 1 and resistor 2. And I'll make a spot over here to give values for that in just a moment. Now I've got resistor 1 and resistor 2. Again, let's just say that my voltage is 12 volts. And we'll list those in just a moment. That's one way that those 2 resistors could be arranged, one right after the other. If you have items electrically that are arranged one right after the other, we say that they are in series. Series means that they come one right after the other with only one conducting path between them or through them. And that's because just like things in a series, like books in a series, or movies in a series, or games in like a baseball series or a basketball series, they come one right after the other. 1, 2, 3, 4, 5, however many there are. And so if you have items that come one right after the other, then those are described as being in series. Now, what if they're not one right after the other? What if you have a branch in your circuit, and maybe resistor number 1 is on this loop, and resistor number 2 is on this loop? Well, you see that here I've got more than one conducting path that they could go through. The electricity could follow the green path and go around this way through the top part of the branch and back. Or it could follow the red path, red and green for Christmas, and it could go through that bottom loop and return back. And so you see that we've got more than one path. It could come through this top path, or it could go through the bottom part of the path. And since you have more than one path, that is what's known as parallel. I'm going to take those paths off the drawing for just a moment. And that's what's known as a parallel circuit. And so that is what's known as a parallel circuit. There we go. And having those in parallel, you have to work that differently than you have to work resistors in series. So right now we are going to set parallel aside for a moment. We'll come back to it. We'll come back to it soon. So that's what a parallel circuit is, but we're going to erase it, and we'll come back to it on the next page. All right, so let's just say that resistor number one is, 3 ohms, and let's say that resistor number 2 is 5 ohms. All right, and we'll take those, and the question is, how much total resistance do I have in this circuit? Okay, well you look and you say, hey, if you've got 3 ohms resistance here and 5 ohms resistance there, that must mean that you've got 8 total. You're just going to add them together. And you would be exactly right. The resistance for the total circuit is what's called the equivalent resistance. Equivalent resistance. And the equivalent resistance is the resistance for the whole circuit. So the resistance for the whole circuit. And since I'm having to write this instead of have it pre-typed, you can probably keep up with me. For the whole circuit. Not just one part, the whole thing. All right, and so the equivalent resistance is the resistance for the whole circuit. And in series, I want to make a point again that this is only true in series. We'll have a different rule for in parallel. In series, and that's 2 words, in series, the equivalent resistance is equal to just adding up all of the other resistors. However many there are. If there's 4, if there's 5, if there's 19, if there's 36, you just add them all up. In this case, there's only 2, and so that's easy enough. You say, okay, Req is R1 plus R2. So Req is 3 plus 5. Req is 8 ohms. Okay? And you say, Mr. Willis, that's great. You've got 8 ohms of resistance for the whole circuit. Why would I possibly need to know that? I'm glad that you've asked. The reason that you would need to know that is because if you're going to find, remember that we're interested in how much current is leaving this battery and how much current is returning to this battery. Well, if you're going to know how much is leaving to go through the whole circuit, you're going to have to use the resistance for the whole circuit. And so in this case, if I want to apply Ohm's law to the whole circuit, I'm going to need to use the value for the whole circuit. So instead of V equals IR, I'm going to type V equals I times Req. All right, so let's see. We said, and let's go ahead and do that. We said that our voltage was 12. And we're interested in what our current is for the whole circuit, so we're going to leave that as I. And we're going to put in REQ as 8. I'm going to click down just a little bit and give us a little bit of extra writing space. Okay. And so V equals I times REQ, 12 equals I times 8. What do we get if we take 12 and divide by 8? Sure enough, we get 1.5. What units? We get 1.5 amps. All right, it is 1.5 amps, and that tells us how much current is leaving and returning to the battery. That's also the amount of current that is traveling through each of these resistors. Now, I have a question. Do you think that it takes the same amount of voltage, the same amount of energy, to push 1.5 amps through a 3 ohm resistor as it does to push 1.5 amps through a 5 ohm resistor? And you think about that for a second and you say, no, there's more resistance here. That's got to take more energy. And you are correct. And so what we're going to do at this point is we're going to apply Ohm's law. We're going to apply this idea to each element, to each part of the circuit. All right? I'm going to erase the definition for equivalent resistance and get us some more working room. All right, and in this case, we're going to find the voltage that it takes for each resistor. And the way we're going to do that is by applying Ohm's law to each resistor. So I'm going to take V equals IR, but I'm going to label it with a subscript of 1 because now I'm applying it only to the first part. V equals I1 times R1. So V1 equals I1 times R1. Now my voltage is going to be, that's what I'm actually looking for because I want to know how much voltage it takes to push my current through there. Up until now, we've always looked for current, but we want to, in this case, we know how much current it is. The current that we have traveling through this is still 1.5 amps because that is the amount that's present in all parts of this series circuit. Okay, so this is 1.5 amps. This is 1.5 amps, and so are these, 1.5 and 1.5. Both of those are amps. All right, we had a question from the audience. The question was, if this is, if we are working for just resistor 1, do we still use this value? And the answer is yes, because that is the value that goes through resistor 1. It's also the value that goes through resistor 2. So we're going to use all these values in order to calculate how much voltage this is required in order to push that through there. So let's see, V1 equals I1 was 1.5, and R1 is 3. All right, and so if we take 1.5 and multiply by 3, see, 1.5 times 3, I get 4.5 volts. And so that means the voltage through number 1 is going to be 4.5 volts. Now there's two ways to find the voltage that's used up then at number 2. One of those ways is just to say, hey, I've started with 12 volts of potential energy. I've used up 4.5 volts of potential energy. Clearly there are 7.5 left. You could do that. You could just do the math. The other way to do it, though, is to apply Ohm's law to the second resistor, V2 equals I2 R2. So let's do that, and let's see if our 7.5 prediction is correct. So V2 equals I2 is still 1.5, and this is the real trick of understanding that you have to have here. You have to understand, once you've applied Ohm's law to the whole circuit and found the current for the whole circuit, you have to realize that that is still what's moving through each of those resistors. Okay, so 1.5 times 5. And sure enough, when you take 1.5 and multiply by 5, you will get 7.5 volts. And that's exactly what we would expect. We would expect you to start with 12 at this end, 12 volts of potential energy. And you're going to have 0 when you return to the other end. That's what it means when there's a 12-volt potential difference. And so you still have 12 volts until you use some of that energy up. And so at this point, you've got 12. You use 4.5, which means at this point in the circuit you still have 7.5 left, but then you are going to use the rest of it pushing through that last resistor and have 0 volts left. And then you'll coast on back to the final pole of the battery. And so that's that. If we wanted to go ahead and calculate the power used in each resistor, we would again apply P1 equals I1 V1 and P2 equals I2 V2. And we would do that using, in order to find P1, we would use I1, which is 1.5, and V1, which is 4.5. So 1.5 times 4.5, how much is that? 6.75? All right, and so when you do the math there, you'll get that P1 is equal to 6.75 watt? That's right, watts. 6.75 watts. All right, and then you can do the same thing for P2. So I'll leave you to finish out that problem. And at this point, we're going to give you a practice sheet that has a few parallel circuits, or excuse me, has a few series circuits. And I want you to, for each circuit, to find the voltage used on each resistor, the current through the entire circuit, the equivalent resistance for the circuit, and the power at each resistor. So let's see, let's make a list of the things that we're going to find. So for each question now that you're given, you're going to find, first of all, the equivalent resistance for the circuit. Then you're going to find the current through the whole circuit. Then you're going to find the voltage drop at each resistor. And then you're going to find the power used at each resistor. All right, and you'll work through that just like we did in the examples. There will also be some parallel circuits drawn on those pages, but just label them as parallel and skip them today. We'll work them tomorrow. All right, I hope you have a wonderful day, and thank you for watching.